Hello everyone, welcome to our presentation. I'm Seong Kim, Assistant Professor at Kyung University. This paper is a collaboration with my colleagues in TU Mini. The title is Longitudinal Quantitative Assessment of COVID-19 Infection Progression from Chest CTs. As you know, COVID-19 pandemic has made a lot of changes in our life. It already infected more than 200 million people and caused more than 4 million deaths in worldwide. In order to manage these diseases, chest CT has played an important role because it can show image patterns such as ground glass opacity and consolidation. According to the study, which was reported in 2020, temporal change of diverse CT infection might indicate progression and recovery from COVID-19. That means longitudinal CT may play central role in diagnosis and management of COVID-19 pneumonia. So our goal is to assess COVID-19 infection progression. As you can see in this figure, the input is 2 CT scans from different time points. If a patient is hospitalized with the disease, it is very natural to take another CT scan after some days. For example, this CT is taken from 1 week ago, and this one is taken today. So we want to build a model which can produce progression map as the live figure. This example shows progression and recovery of consolidation, which is known as most severe symptom from COVID. In order to calculate progression map, we segment pathologies in each CT using longitudinal segmentation net. It takes registered pair of CTs. Then by simply conducting subtraction, we can get progression map. This example is for consolidation. So we first get binary map from pathology mask, which denotes consolidation and non-consolidation, and we do subtraction. It can be, of course, used for other pathologies. For longitudinal segmentation, 2.5D segmentation model, which is built based on fully connected dense net, is designed where 2 CTs are concatenated as input. Spatial-temporal cues from 2 CTs are encoded to improve the segmentation on target city. Results from 3 different views are aggregated in order to produce biometric results. As you can see in this figure, fine-grained multi-layer pathologies, including ground glass opacity, consolidation, and fluid effusions are segmented. Also, registration is important to exploit spatial-temporal cue in the longitudinal segmentation model. Also, obviously, in order to calculate progression map with simple subtraction, it is required. For this purpose, we use long mask-based method. It is pretty easy to get the long mask. So the deform over period from long mask is calculated and it is applied to CT for the registration. These are qualitative results for our model. As you can see, for the pair of CTs, we can segment fine-grained pathologies. And also we can do progression analysis. Based on our model, we can address the following research questions. Can longitudinal CT be used to improve segmentation and progression modeling? Can you encourage the model to exploit progression information during training? Does the form of registration play a role? These are results on progression. We calculate DICE as a performance metric, and this table shows the answers for the question. It was effective to use longitudinal information from segmentation model for predicting better progression map. Also, we use progression loss, which is designed based on progression map as additional supervision during training. It was also effective as we can expect. Also, we outperformed 2 baseline methods. These are segmentation results and ablation study, which can provide answers for previous questions. You can find more details in our paper, and we can discuss them during our poster session. So this is the end of my presentation. I'm looking forward to meeting you on MICCAI. Thanks a lot.